You should be standard W1, right before example 4, we left off. We're talking about something called the natural base and also something called continuously compounded interest. The definition of the natural base is this letter E that's approximately equal to 2.718. Okay. And so when you see this E in math from now on, you know it's going to represent this number. Much like pi, when you see pi, it represents the number 3.14. The reason that sometimes numbers are assigned symbols is because they occur so frequently, or they always occur in certain situations. For pi, pi is always 3.14 because pi is the ratio between a circumference and the radius of a circle. And so because it's the same no matter what circle you have, we just assign it a symbol so that we can use it without rounding every time. E is the same way. E is called the natural base because it occurs very frequently in nature. This ratio, 2.718, in one way that it occurs is with a sunflower. The ratio of the number of seeds in the sunflower head to the circumference of the sunflower, or it's either the circumference or the area. I think it might be the area. That ratio of the number of sunflower seeds in the head of the sunflower to the area of the sunflower is 2.718. The ratio of an arm bone to one of your leg bones is 2.718. There's a lot of other situations where this number kept popping up. And so the guy who noticed this pattern, his name was Euler. That's why it's called, or that's why the symbol that was picked for it was E, because he's the one who noticed it. But it's called the natural base because this number occurs very frequently in nature. And so often you'll see it now as a base of an exponential. So instead of having something like 2 to the x minus 2, sometimes we might have e to the x minus 2. It's the same type of problem. It's just the e represents this number with decimals. So we could still punch it out on a calculator. If you look to the calculator, you'll see a couple buttons that have e to the x or just e. So, yeah, just want to forewarn you that you're going to see this natural base. And again, this is just a number that pops up, especially the exponential type situations, a number that occurs very frequently. Where it plays a part for us here in this section is something called continuously compounded interest. So this is interest that isn't assigned every year or every quarter or every month, but it's continuously compounded. So you're continuously getting a little bit of your interest all the time until it adds up to however many interest you have at the end of the year. The formula for this is going to look similar to the one that we had over here with the p. We're going to have the p, but instead of the base of my exponential term being this 1 plus r over n, the base is going to be e. So you have principal, you have e, and then we're raising it to the exponent of rt. I often will refer to this as the PERT formula. P is your principal, R is your rate, make sure you're in decimals, T is your time. Because if there are two words together, those two words are continuously compounded. If those are in the problem that you're doing, then you know you have to use the PERT formula. So when we look at example 4 here, that is what we're going to see. For example 4, Kayla can't believe her good luck. She just found $20 in her locker and got a call from her investment broker that he has found a mutual fund that continuously compounds at 5.3 interest. She sprints down to his office and deposits that $20 into the account. How much money will she have in the account 40 years later? Now, because these two words are put together, it's not just compounded, but continuously compounded, I know that I have to start with this formula. The P is my principal, which was $20. The rate is 5.3. And then I want to see how much money I'm going to have after 40 years. So if I punch that into the calculator, 20 And then your E button is second, and then under the ln, so there we go, and then 0.053 times 40. You end up getting $166.62. Now, it doesn't seem like a lot of money after 40 years, but when you look at the comparison between what you started with and where you ended, if this number was 2,000, let's say, or even 20,000, that's going to be a huge difference. So just look at in proportions. Well, we could actually set it up as a proportion. You have gained 8 times more money in 40 years. That's not touching the 20 bucks. That's just with continuous compounded interest. You'd have 8 times as much money. Okay. Now, the next part is type 4 problems. For type 4 problems, and this, I labeled it as a 4 here, you're going to start by writing the original function, because with these type 4 problems, we're basically taking a function they've already given us and breaking it apart so that I can see the rate. So you write the original function and use the power of a power property to rewrite the exponent. The next thing that we do then is evaluate the power, which punched out in a calculator, and write it in the form that we're used to. Okay, so this is basically working backwards again. They're giving you a function and you're supposed to back it up until you can find the rate that they had at the very beginning. Okay, let's look at a couple of examples here. For example 5, I'll work my way down. You start by rewriting the function. Okay, so they give us this function 100 times 1.08 to the t. T is in years since 2004, and we're supposed to find the approximate monthly percent increase in sales. So we start by saying, okay, monthly increase in sales, I can't change the t. Like, I can rewrite t as much as I want, but I cannot change the value. So however I rewrite the exponent, I have to make sure it's still really worth 1t. But to write it in terms of how much I'm getting per month, there's 12 months in a year. So I rewrite my exponent as 1/12 of a year. So 1/12 times 12t. Now normally power and a power, you multiply the exponents together. So actually what I'm going to do now is stick this guy inside the parentheses. Basically reverse the power and a power property to get a new base value per month. Now, in rewriting it, basically you're going to be adding or subtracting 1. In this case, we would have had to add that decimal to 1 to get, your 1 plus r. So, in terms of monthly increase, you're increasing at a percentage rate of 0.64% every month, instead of every year increasing 8%. That's how much you're increasing every month. Okay, here's another example. The amount in grams of a radioactive isotope after T days is given by this function. What percent of the chromium 51 decays each day? Okay. Notice that, our variables are the same. We have days, so I don't have to do anything funky with the exponent here, except I want to get it into this rate, or this formula here, so I can clearly see what my r is, since that's what it's asking for. So I have to get rid of the 28 on the bottom, which means I'm going to bump the 1/28 into the parentheses and punch it out to get a new decimal. And then I get this, and to get it back to 1 plus or 1 minus, I have to take that away from 1 to see what I would have had to have here to get 0.9755. And so 1 minus 0.0245 gives me that expression. And what that does is give me my rate which is 2.45% that would decay each day. One last example. Interest rate needed for the balance of an account to double every 15 years. Okay, so every 15 years we want it to double. 2 is my base. I'm looking for my interest rate. So I'm trying to get it set up into the 1 plus or 1 minus r. Because it only doubles every 15 years, I have to take my time, my years, and divide it by 15 to represent what's going to happen every year to get to that doubling after 15 years. Bump the 1 over 15 in with the 2, punch it out, and then split it apart into 1 plus or 1 minus. In this case, it's 1 plus. So you're increasing at a rate of 4.73% in order for the account to double every 15 years. Okay. Now, just so you know where we're headed on Monday, we will be practicing standard W1 quite extensively on Monday. And then we will jump right into the next section as well, which has to do with logarithms. And I think after that we have a couple more, and we'll be ready for that. So, hope you're having a good weekend. This is Chris Cross signing off.